Hello, my name is Emma Topolcsik. I'm a master's student at San Diego State University in the Computational Science program. I work with Dr. Pablo Machuca, and today I will be talking about autonomous optical navigation for spacecraft in the Earth-Moon system, specifically modeling and understanding its limits. So autonomous optical navigation is important because lunar missions benefit from low cost and performant navigation methods. Your traditional ground antenna communications come with higher cost, more equipment on board, and limited accessibility. This is where optical navigation comes in. A method of horizon-based position estimation algorithms that we are looking into is called centroiding, shown in the process below. The algorithm detects the horizon of the moon for edge detection. An ellipse is estimated where the center is denoted by the red dot on the furthest right. This is the estimated center of the moon. And with this information, the algorithm can measure the range and the direction of the spacecraft from the moon's estimated center. We want to investigate the performance and effectiveness of this process, but image processing and Monte Carlo simulations are very computationally expensive. So we ask, how can we efficiently incorporate optical navigation measurements into Monte Carlo simulations? So the model that we've come up with starts with image generation for a variety of ranges, directions, and moon phases. And for each of those positions, the image generation includes 100 different computations with various random noise. The image processing is performed, and the output includes a measured range, direction, and statistical values for these 100 images. The drawing in the middle shows the true direction, which is dotted with the blue line, versus the measured direction, and how these measurements have error, which results in a margin of possible moon centers, which is the circle that is drawn on to the right of that, which is dependent on an angle theta. From the image processing, we can generate a lookup table of the results and interpolation approach to model these errors obtained from the image processing along any trajectory of choice. From there, we can enter a Monte Carlo simulation for random theta values using data from the lookup table, which implements a Kalman filter. From there, we obtain the navigation accuracies along the trajectory of interest, and then we repeat for any other trajectories. So what is involved? So the image generation depends on 4 parameters. So the first one is range, which is the relative position between the spacecraft and the moon. The second is 2 direction angles. So I guess it's the next 2, which define the direction that the spacecraft is pointing at. And then the moon phase, so the time is very important because the moon, as the moon phase changes, the way the image processing tool performs is different. As for the Monte Carlo simulation, it implements a Kalman filter, which is an estimation algorithm that uses measurements over time, computed from the image processing tool, to converge to the closest true position. So this process requires a dynamic model of the physics, and we are using the circular restricted 3-body problem. It uses the sensitivity matrix of this equation, which is taking the partial derivatives of the circular restricted 3-body problem with respect to each initial state. It's a very complicated 6x6 matrix, so we are not going to include it on the PowerPoint slide, but it is important to understand where that matrix comes from. As for the goals and the current efforts that we have, so the lookup table is the end goal, and it will be a 4-dimensional lookup table that is dependent on the range, the 2 angle directions, and the moon phase. The current efforts include bridging that gap between the results from the image processing to the Monte Carlo Kalman filter simulation, which has been my core effort right now. And the preliminary results below show a simulation of the Monte Carlo Kalman filter. And this is for some random number of measurements, and it shows the distribution of error in the first image, and then the second image shows the evolution of the mean error over the Monte Carlo simulations. I look forward to discussing this more at the ACSESS event at the end of March, and I look forward to seeing you there. Thank you.